opportunity that we all have to do this research and to come together here to discuss it. And I'm following on from the last two talks, particularly Sagato gave a lovely introduction to the physics that we're excited about. We want to test experimentally if gravity can be something that can entangle things, test if gravity can be in a superposition. We want to know if space-time can be in a superposition. We're asking, what is the gravitational effect from a mass in a superposition, experimentally. And we've got this great team of five of us, 5 PIs who are here, plus our research groups, of course. Here's the 5 of us. We've got Andy and Anupam and Sagato and Dave, and we've got a combination that splits up into theory and experiments. So we have these 3 experimental groups, 3 different experiments in Northwestern and Yale and in Warwick in my lab, and this amazing, tight collaboration with theory with Sagato and Anupam. And our project is called Macroscopic Superpositions Towards Witnessing the Quantum Nature of Gravity, MAST-QG. And as Sagato was saying, this is the concept that we're excited about. We want to have this superposition of a nanoparticle in a superposition of being in 2 places. It's doing some matter wave interferometry. And then we would have a second one, and we would be looking to see if gravity can entangle these 2 systems, and if it can, subject to assumptions like the fact that gravity requires a mediator, then that would be evidence that gravity is quantum in this sense. And from this 2017 paper, we get these rather tantalizing looking parameters where you would envisage a 2-micron object. This delta x is the superposition distance, could be 250 microns, 200 microns closest approach to avoid things like the Casimir effect dominating. And the experiment, it would take a second or 2 for this entanglement. These numbers might seem naively reasonable, but actually they're extremely challenging. This sort of huge superposition distance is hugely challenging. So this is a very ambitious experiment that we're working on, and I want to show you the progress we're making towards it. So I'm going to cover these 4 things. We'll talk about this cryostat for free-fall experiments in Northwestern. We'll talk about the amazing nanodiamonds that my team in Warwick has made. We'll talk about how we have to reduce the electromagnetic background. So if we're going to look to see if 2 diamonds can be entangled through gravity, it's crucial that we can be confident that they're not getting entangled through something else, through electromagnetic interactions. And I've got theory developments as a last piece, but actually you'll see on all the slides there's theory developments referenced as they relate to all of these experimental bits of progress. So let's start with talking about this low vibration cryostat in Northwestern. This is specially designed in Andy's lab. It gets down to 4 Kelvin. Of course, that's great for the vacuum as well. You have to have great vacuum to avoid decoherence from the gas atom collisions. The vibrations are below a nanometer at 10 hertz, which is awesome. This is using some of the great tricks from the gravitational wave community, and they have been able to trap silica and diamond nanoparticles in this vacuum, which is a great start. And here's one of these theory papers which is supporting some of this work. And in terms of cool stuff that Andy's group's going to be doing with this, it's quite exciting. He's going to be trapping one of these nanoparticles, dropping it in free fall. It's going to go through a grating, an optical grating. It's going to do diffraction and then be detected down here, 20 centimeters or so down. And that should lead to a diffraction pattern. So this is time on the x-axis. And so pick some time and you get a slice here with fringes. But doing this kind of thing with a nanoparticle has never been done. So the record comes from from Marcus Arndt's group, where they've done it with molecules that have got about 2,000 atoms in them. So this would be 1,000 times larger object. Demonstrating this wave-like behavior would be incredibly exciting, and is on top of all of these sources of decoherence, like the gas and the black body light being emitted by the nanoparticle and the vibrations of the equipment. And so this is really exciting. There's this paper looking at the theory paper looking at the decoherence due to the air molecule scattering. So this is super impressive, but actually is not big enough, not a macroscopic enough superposition for this gravitational entanglement. This is a great step, but we need to then go another 3 orders of magnitude up in mass and also a larger superposition distance. So here, in this experiment, the superposition distance would be, say, hundreds of nanometers, but we're going to need more like 10 microns to test the quantum nature of gravity with this gravitational entanglement. And so that's a really ambitious feat. But so we have a bunch of theory proposals showing how we want to do that. And they go back to this 2013 work that we heard about earlier, and it involves the Stern-Gerlach effect, just like Ron was beautifully introducing. So we want to have a nanodiamond with a single electron spin in it, and we want to take it on this closed-loop Stern-Gerlach interferometry. And so, in our calculations, this should let us reach this large superposition distance that we need for the gravitational entanglement. Here's a new theory paper. All these theory papers are sort of new stuff that our team has done during this MAST-QG project that we're all part of at the moment. So here's one of these nanodiamonds. It's optically trapped in vacuum in my lab, and you can see it's a nice, pretty green dot. But the optical trapping causes problems. With this optical trapping, you're focusing a lot of light, maybe a watt of light, onto this diamond, and then it's taking in too much heat, and it just absorbs a little bit of that light, but that overheats it in vacuum. And so that turns out to be not a good strategy. But we have 2 solutions to that problem of the overheating. So one of them is that we have gone from this nasty type of diamond to this much more clean diamond. So this is 1,000 times improvement in the purity of the diamond, so that it's more transparent, so the laser light doesn't get absorbed so much. And the diamonds that look like this, we get my friend Ollie to mill them up into nanodiamonds, and so they look like this, and then this is way nicer for these experiments. And as I'll show you in a sec, we've now taken this down just recently by another 2 orders of magnitude down to 1 part per billion of nitrogen impurities. But so for avoiding the heating, the other part of the puzzle is that we need to do magnetic trapping, diamagnetic trapping. So this is a diamagnetic trap in my lab where we have a sharp magnet here and another one at the top, and this twinkling thing in the middle is a diamond that's nicely trapped there in vacuum, and that's great because the magnetic trapping isn't pumping heat into the diamond. So, because this diamond needs to be long-term for gravitational entanglement, the diamond needs to be at 1 Kelvin or so internal temperature to avoid it emitting black body radiation, which would collapse the superposition, reveal its position. Here's a theory paper from us about the magnetic noise in this Stern-Gerlach experiment. But so the fact that we improved this purity of the diamond has another great consequence, which is in the spin coherence. So here's an electron microscope picture of one of our diamonds, and here you can see we're measuring the fluorescence, the light coming off the NV center after we excite it, and I love how you can sort of see that they match up nicely. That means we know we're looking at this diamond, and we can measure the spin coherence. We get the longest times that people have found in the literature for this spin coherence. Here's a more recent updated version of this where we did it with carbon-12 isotopically pure diamond, And we beat our record, and now we have the longest T1, T2 star times, the longest quantum coherence times for these, for electron spins in nanoparticles, because during this whole interference, then the NV spin state has to maintain its quantum coherence, of course. So this is great, and we're taking it further now by, like I said, using even purer diamonds with 1 part per billion of nitrogen. We're fabricating a bit like on Ron's slide. We're fabricating lots of diamonds with a particular size and shape. And then a cool thing that we've done here in this video, you can see that we've attached a metal tip to one of these diamonds and chopped it off using focused ion beam, and then we're moving it in this video. This is the diamond here. This is the metal tip. And we're just moving that diamond around, and that means that we were able to do that and place 3 of them down into chosen positions. And then this is going to lead to us being able to deterministically make a beautiful diamond, check that it's got a nice NV center in it, and then put it into a trap so that we can be using the best possible diamond. Okay, and now let's move on to talking about these electromagnetic backgrounds. This is work from Dave Moore's group in Yale. And we know that if we have 2 of these diamonds and we're trying to look for some gravitational entanglement between them, we mustn't have any electromagnetic forces causing that entanglement, which would otherwise fool us. And so even if we have a single electron net charge on each of them, that would give us a potential energy that's 10 orders of magnitude bigger than gravity. And so that's a complete, that would be a showstopper, but that just means we have to have the same number of electrons and the protons on these particles. They have to be electrically neutral. This has been demonstrated by Dave and Andy over the years that this works. But then, so you're left with 2 neutral diamonds, and you're looking at their interactions, but still, you've got to then worry about electric dipoles, because you've got 10 to the 14 or 10 to the 12, 10 to the 14 atoms in here, and if some of the electrons are over to one side, then you've got an electric dipole, permanent electric dipole moment, and it's known from Dave's work with silica that this is ubiquitous, unsurprisingly perhaps. And based on those estimates with silica, you might expect that the electric dipole moment would give you 10 to the 6 times bigger potential energy than gravity. So that would also completely kill you. But so we have, and this hasn't been measured in diamond, and so we're going to be looking forward to Dave's group measuring that, and we have some great plans to fight it on the next slide. But also, one of the ways that we'll fight that is by having a shield, having a conducting shield in the middle, a superconducting shield, most likely, so that we've got a diamond on one side, a diamond on the other, and the shield certainly can't shield gravity, but it shields electromagnetic things quite well. What you're left with, of course, is interactions between the particle and the shield, and so we need to then study that and reduce the effects of that. But so yeah, back to the dipole moments. So Dave's group has built this novel magnetic, it's a hybrid trap, which is diamagnetic and combined with some optical trapping. That lets them get down to high vacuum and without suffering from the heating that you get in optical traps. They're starting to do the electrical neutralizing it. They're starting to electrically neutralize these particles. They've done this brilliant feedback cooling, so the particle would be moving around in 3D with simple harmonic motion, but with feedback cooling you can reduce that motion a great deal. And they've been spinning the diamonds, which is super cool. This is great for talking about Ron's point about the issue of problems with rotations. It can be valuable to be spinning the diamonds, you can get a gyroscopic stabilization. We have a theory paper on that on another slide. But so these are all nice bits of progress. And yeah, this was a video. I don't know if you saw the video of this diamond moving. You can see that it's moving about before the feedback cooling starts. So here, Dave's going to look at the measuring how big these electric dipole moments are, which isn't known in silica. I mean, well, it's known in silica, it's not known in diamond. And in order to fight that, then we have these plans like rotating the diamonds. Also, we're going to try annealing the diamonds in the trap to see if we can fix the permanent dipoles, and of course, improving the quality of the material. And there's also this cool stuff where you can average it away using even more intelligent plans than just spinning it. Here's a nice picture of two of these diamonds in one of Dave's traps, which is leading towards this measurement of the strength of the interaction with the dipole. Yeah, here's this theory paper looking at the how spinning the diamond can help with dealing with some of these problems of the orientation. And then now just got a little bit of time to tell you about work on this screen. And so this, like I said, we want to have a screen to shield the electromagnetic interaction. Here's a theory paper from us on that. And in Andy's group in Northwestern, then they've got some great data now where they've brought a screen. It's a metal mirror up close to an optically trapped nanoparticle. And then this means that they can start to measure the interaction between the levitated nanoparticle in vacuum and the screen. And so, as you can see, and they have a nice archive paper on this. Here you can see how at first the particle traps a little bit further away from the screen, but then they can push it, they can make it move so that it sits in this node as close, the closest position to the screen, determined by the wavelength of the trapping light. So it's about 550 nanometers from the screen. This is measuring the natural frequencies of of this nanoparticle, and they can cool. Again, they can do this feedback cooling trick where they reduce the amount of the motion so that the particle is in the right place. Almost done. This is just a summary of all the theory papers, including a nice RevMod Phys review. And we had this white paper that brought together 40-odd people, including Gurudev and Ron and other people. And these are the conclusions. So I was showing that there's this nice low vibration 4K cryostat, long spin coherence in nanodiamonds, moving these diamonds around, and feedback cooling inside of the hybrid magnetic optical trap, feedback cooling next to a screen, and I'll leave the 3-year goals up so that I can end there and say thanks for your information. Thanks for your attention.